Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to look at a topic in trigonometry, and it's going to be specifically a topic on identities. So for that case, we're going to see how these expressions that are used to, of course, find out whether the quantities are equivalent, and also used to simplify some of the expressions that we may encounter in our problem solving insofar as trigonometry is concerned. So without further ado, thank you and welcome. So as I've said, today we're going to look at trigonometric identities, and of course, basically these are expressions that satisfy every member for which both sides are defined. For instance, we we had looked at the concept of a unity circle and tried to do some of the analysis, of course, which we are going to mention in case there is need. So for this, I'm going just to draw an illustration that's going to guide us into the concept of trigonometric identities. So in this case, this is trigonometry, and we're going to learn about identities. So when when we were trying to discuss about the unity circle and the concept of trigonometry, we're just given an illustration of this kind that suppose there's a array that is maybe a point in this rectangular coordinate system that is moving at an equal distance from the center, and then we can be able to define this particular point or the extent of motion by describing motion in x and y coordinates, and then this distance is represented by r, and of course the angle to which that particle moves from this point to that one, it forms angle theta. So when we were trying to look at the analysis of the unity circle of course is a circle which this is OP is equals 1. 1 is a unit. So in this case we're going to look at that, and the relationship that came about from this is that, just try to limit this. So the relationship that came about from this is that we had a Pythagoras theorem, whereby we saw that we can be able to represent this specific x and y distances in specific ways. Now from Pythagoras theorem, we stated that x or r squared is equals x squared plus y squared, and that one gave us a different way in which we can be able to represent the x and y extent to which this particle has moved maybe into dimensional space. So this one we can be able to illustrate it using the angle that has been formed, which is angle theta, using this acronym that we had mentioned when we were talking about trigonometry, in that we can describe it in the form of maybe the sine, the cosine, and the tan of theta. And we said that the tan of the sine of theta, of course, can be given as opposite. So this is opposite in reference to this angle, so it is y, the ratio between y and x. No. This is the ratio between opposite and hypotenuse, which basically is r, whereas the cosine of theta can be represented as adjacent over the hypotenuse, which is x over r. So basically, in this sense, we said that we can be able to relate these equations and make y the subject of the formula. So implying y is equals r the sine of theta, and for the second case, x is equals r the cosine of theta. And therefore we said that given that we have this equation at this particular point, we can be able to do a substitution for x and y and try to see which kind of an expression we can be able to get. So from this, I hope that we just do away with this. So r squared is equals, so we do a substitution for x and y respectively for these values that we've attained there. X squared, so r squared, the cosine of theta squared, plus y squared, so it is r squared, the sine of theta squared. So this one we factor r squared out, cosine squared plus the sine squared r. So we can just do a division for r squared here, and then we find 1 is equals the cosine squared theta plus the sine squared theta. So this one gave us an expression that of course we just have just written on the board. Now this expression forms what we call an identity. So I'm going to write it somewhere from this unit circle analysis so that we're going to use it somewhere when we come across it. So I'm just going to put it somewhere, which is the sine squared theta plus cosine squared theta equals 1. Okay. So from there, that then we're going to see that we had already defined some of the, let's go into this, inverses of trigonometric functions, in a sense that we said the tan of theta is equals the sine of theta all over the cosine of theta. And then number 2, we said there's an inverse, an identity, there's also a ratio for the inverse over tan, which is given as the cot of theta. 1 over tan theta is equals to the cos of theta. So this is number 2. And then number 3, we had another one which was sec x, which is given as 1 of the cosine of theta. Sorry, this is a sec theta. So therefore, and lastly, we said that the cosec of theta is given as 1 over the sine of theta. So therefore, from this we can be able to see that from the identity that we have written for that particular expression, we can be able to do a manipulation of that expression and try to see whether we can be able to find other representations of that specific identity. So suppose I divide every side of this expression by the sine of theta squared, or the sine square of theta, plus the cosine, okay, plus the cosine square of theta equals 1. So I divide both sides by the sine of theta over the sine square of theta all over the sine square of theta. So we said whatever you do on the right, you do it on the left, so that you do not interfere with the value of that expression, so that it is mathematically correct. So we have 1 plus, so the cosine of theta over the sine of theta is the inverse of this. So basically this will be 1 over, of course, the tan squared theta, which is equivalent to 1 over the sine squared theta. So if we try to see at this particular case, the first part of it is given as 1 plus, so the inverse of tan is cot. So therefore we're going to have a square of cot there. So this is the cot square theta is equals, and then the inverse of sine is going to be cosec. So the cosec squared theta. So therefore 1 plus cot squared theta equals cosec squared theta. So this is a division by the sine of theta from the first identity. So therefore this is going to give us another expression. And I'm going to write it somewhere because of space, so that we're going to use it somewhere. So I'm just going to do away with this. So I'm going to write, okay, this is equals 1. Maybe I minimize the space still. So the sine squared theta plus the cosine squared theta equals 1. I've got another one, 1 plus the cot squared theta equals cosec squared theta. Okay, you can continue from there. So therefore, you can just do away with this one. And suppose we divided both sides by the cosine squared theta, which we have already mentioned. then we can be able to have plus the cosine squared theta equals 1. Now divide both sides by the cosine squared cosine square of theta, cosine square of theta. This is going to give us sine square theta over the cosine square theta is tan theta, so it's going to be the tan square theta plus the cosine square theta over the cosine square theta is going to give us 1, and this is going to give us 1 over the cosine. The inverse of cosine is sec, so therefore we are going to have sec squared theta. So from this expression, if we divide both sides by the cosine squared theta, we're going to get that expression, and therefore I'm going to also write this last expression somewhere so that we can be able to use it. So this is the tan squared theta plus 1 is equals sec squared theta. So we have found 3 expressions for the first, second, and third for those particular identities. Now expression 1, suppose I take this one as expression 1, we just use a different illustration for that. Now suppose I take this one as expression 1, and this one as expression 2, and this one as expression 3. The expression 1, 2, 3 represent what we call, sorry for that. The expression 1, 2, 3 represent what we call the Pythagorean identities. So this one, so they represent what we call the Pythagorean identities. And as we said, these identities are very much essential, especially in trying to deal with problems that involve trigonometric functions, in that they are used to simplify expressions and also to determine whether expressions are equivalent. So in this case, we're going to do a few of the examples to try and prove whether maybe an expression on one side is equivalent to an expression on the other side. And this is known as proof of identities. So therefore we're going to use the Pythagorean identities to try and solve problems that of course fall under this category of trying to prove whether the identities are actually the same. So in this case, I'm going to have a sample question to try and prove whether these identities are of course equivalent. Now suppose you are given an expression like this, 1 plus sec x, and then the sine of x, the tan of x. This is the product between sec x, sine x, and tan x is equals sec squared x. So in actual sense, for this case of our problem, we are going to justify that the identity, or maybe the expression on the left side of this equation, is equivalent to the expression on the other side of the equation. So we're going to just try to figure out and manipulate, or maybe substitute for whatever we have found using these Pythagorean identities and the inverses in this expression to try and find out whether it's the same. So in this one, the first step that we're going to do is to take this first part of an expression, say that therefore it is 1 plus sec x is equivalent to the inverse of cosine. So it's therefore going to be 1 over the cosine of x. And then for the second one, we can just retain it. I'm just going to change this one into basic identities. And then we are going to have the tan of x is equivalent to the sine of x over the cosine of x. So we are going to have this one as the sine of x over the cosine of x. So trying to simplify this expression, we're going to get that it's 1 plus, this is the sine squared of x divided by the cosine square of x. Therefore, in this case, when we are trying to do basic mathematics, sometimes we do what we call least common, or maybe the LCM. In this case, we're going just to look for a common factor that's going to be used for the denominator. And this one, of course, can be used to assist us find out exactly what this one represents. So if I try to do this one by making the cosine of x the common denominator, therefore, this is going to be cosine squared x plus the sine squared x. But we have already defined this one as the first identity in the Pythagorean identities. So therefore, this is going to be 1. The sum of these two is going to give us 1 over this cosine squared x. Of course, which is going to give us the inverse of cosine is sec. It's going to give us sec squared x. So we were requested to define whether the part of the expression on the left hand side is equivalent to the expression on the right hand side, which of course is going to give us that. So that process is what we call the proof of identities. Now in this case, we're going to have a second sample question and try to see whether it is also applicable in that particular case. So therefore, I just have sample question 2, and which states that the cosine of alpha over 1 minus the sine of alpha is equals 1 plus the sine of alpha all over cosine of alpha. So we are trying to prove out whether this first part of the expression is equivalent to that second one. So we will write this one and say cosine alpha all over 1 over sine alpha, and then we can multiply this one by the, so this basically is equivalent to multiplying a particular maybe expression or factor, particular expression or mathematical expression using a coefficient on both sides. So if I multiply by 2, divide by 2, it just be the same as 1. So I just multiply both sides by, I mean for the denominator and the numerator using this expression. So therefore, if you look at the second one, or the denominator is going to give us a difference of square. So therefore, we are going to have the cosine alpha into 1 plus the sine of alpha divided by, it's a difference of, so it's going to give us 1 minus the sine squared alpha. And if we simplify this one from the first identity, we're going to see that this is equivalent, for the numerator is going to be equivalent to the cosine of alpha. So therefore, I just pick it from there, do away with this one on the right. So it is the cosine of alpha 1 plus the sine of alpha all over 1 minus the sine squared alpha. So I just do away with this. We proceed from there. So the last one I've said for the numerator is going to be equivalent to the cosine square. So therefore, I'm going to have cosine alpha plus cosine alpha sine alpha all over cosine square alpha. Now this is going to simplify into cosine alpha into 1 plus the sine of alpha all over cosine squared alpha. Now still we will simplify this one. It's going to give me 1 plus this one will cancel with this, so it is 1 plus the sine of alpha all over cosine alpha. Now that I've cancelled 1 cosine, so therefore the identity they requested us to find whether, so this is our answer for this case in trying to solve the first, the left part of the equation, and the identity they requested us, or the expression had requested us to prove whether cosine alpha all over 1 minus sine alpha is equivalent to 1 plus the sine alpha all over cosine alpha, which basically we have already proved that that is the case. So in this case, that is the concept that we were trying to look at, trying to find the identity. The identity of the Pythagorean identities that we have already listed on the board, and we have tried to use them and try to manipulate the figures around and see whether it's basically the equivalent of the other side. So that is it for today. Thank you guys. Bye. God bless.